Hello everyone, and welcome. Today, we're going to explore the fascinating components of a circuit. The title of our presentation is Exploring the Components of a Circuit, and there's a subtitle that highlights the basics of how circuits work. In this session, we'll cover what circuits are, their key parts, and how they come together to make electronic devices function. I'm excited to take you through this journey, so let's get started. Today, we're going to explore conductors and insulators, which are fundamental to understanding how electrical circuits work. You might wonder, what exactly happens in a circuit? Well, a circuit is a complete pathway that allows electric current to flow. This flow depends a lot on the components we use. So, we'll look at the key components that make up an electric circuit, like wires, batteries, switches, and loads. These components work together to control and direct the flow of electricity. When we talk about an electric circuit, we're referring to the entire setup that enables this flow. Think of it as the highway for electricity. And today, our main focus is to understand how these components interact and what roles conductors and insulators play in making circuits safe and efficient. By the end of this, you'll see how essential the right materials are for designing effective electrical systems. So here's the question: circuit or circus? Looking at these options, we have three choices: A, B, and C. Now the big question is, which of these circuits would actually work? Think about it. What makes a circuit functional? It needs to be complete, connected properly, and capable of allowing current to flow without interruptions. Sometimes, what looks like a simple connection can actually have a hidden flaw that makes it non-working. So, as we analyze these options, I want you to consider the importance of proper connections and the overall design. Remember, in the world of electronics, a circuit that looks good on paper still needs to work in practice. This slide challenges us to think critically about what makes a circuit viable versus just a visual or a circus. So, let's keep that in mind as we move forward and examine each option carefully. Let's take a look at our answer key and think about whether these examples would make good circuits or if they are more like circus acts. First up, we have a metal screw. Now, a metal screw is actually a conductor of electricity, which is a good thing for a circuit. But remember, for a complete circuit to work, we also need a power source, like a battery or a power supply. Since that's missing here, this setup wouldn't work as a circuit. Next, we have a plastic toothbrush. Plastic is a non-conductor, so it doesn't allow electricity to flow. Plus, there's no power source connected, so this one definitely isn't a working circuit. Finally, a plastic comb, similar to the toothbrush. Plastic doesn't conduct electricity, so it can't be part of a functioning circuit either. The key idea here is that for a circuit to work, we need a good conductor, like metal, and a complete loop that includes a power source. Without both of those, it's more like a circus act, something that looks like a circuit but isn't actually functioning. By the end of this lesson, you'll have a clear understanding of how to tell apart conductors from insulators. We'll also explore what actually happens inside an electric circuit, making it easier to see how electricity flows. I'll help you identify at least three key components that make up a circuit, so you can better understand how they work together. Lastly, we'll describe what an electric circuit is, essentially, a path that allows electricity to travel from one point to another. These concepts are fundamental because they build the foundation for understanding how electrical devices and systems operate in our daily lives. So, by the end, you'll be more confident in explaining and working with electric circuits. It should be constructed in an unbroken loop, creating a complete path through which electric current flows. When we talk about the direction of electric current, we're referring to the flow of electric charge within a circuit. So, what is an electric circuit? Essentially, it's a closed path that allows electricity to travel from the power source through various components and back again. This continuous loop is crucial because if the path is broken anywhere, the flow stops and the circuit won't work. Recognizing this unbroken loop helps us understand how electrical devices operate reliably. It ties into the overall theme of understanding how electricity moves and powers our everyday tools and systems. Let's take a closer look at the basic symbols and components in an electric circuit. A simple circuit typically consists of three main parts: a battery or another power source, a light bulb or some other load, and conducting wires that connect everything together. These components work together to allow electricity to flow and perform work, like lighting a bulb. Now a key question is, what makes an electric circuit complete? Well, for the circuit to be complete, the electrical path must be continuous, meaning the current can flow all the way from the source, through the load, and back again to the source without any breaks. If there's a gap or break anywhere in the circuit, the flow of electricity stops and the circuit stops working. This idea of completeness is fundamental because it connects all the parts together, creating a closed loop where energy can circulate. Understanding this helps us see how circuits are designed and troubleshoot issues if something isn't working. Remember, a complete circuit is the foundation for everything else we're going to explore about electrical systems. Let's take a closer look at some common circuit components and their symbols. Here we have a fuse, which is a safety device that protects the circuit from overcurrent. Next is the motor, which converts electrical energy into mechanical motion. Then there's the resistor, used to limit current flow within the circuit. We also see the open switch, which is a switch that is not completing the circuit, so current can't flow through it. Conversely, the closed switch is one that allows current to pass, completing the circuit. Finally, we have the battery, which provides the electrical energy needed to power the circuit. These symbols are essential because they help us understand and communicate how different components work together in a circuit. Recognizing these symbols allows us to read circuit diagrams accurately and troubleshoot effectively. Remember, each symbol represents a specific function, and understanding these is key to mastering circuit design and analysis. So, what actually happens in a circuit? Well, these electrons are already present in the wires all around us. They're like tiny charged particles just waiting to move. When we connect a dry cell, like a battery, it gives what we call a push. This is the energy needed to get those electrons flowing in a loop. And as these electrons travel through the circuit, especially through a load or receiver, that could be a light bulb, a motor, or anything that uses electricity, their energy is transformed into other forms. For example, light, heat, or sound. This process shows how electrical energy can be converted into various useful outputs, which is a key part of understanding how circuits work in everyday life. It's all about the flow, the push, and the transformation of energy. Let's think about how to connect these components so that the bulb does not light up. If we want to prevent the bulb from lighting, we could, for example, connect the wire in a way that breaks the circuit. Remember, for electricity to flow and light the bulb, the circuit must be complete. If there's a break somewhere, like a disconnected wire or an open switch, the current can't pass through and the bulb stays off. Now, on the other hand, if our goal is to make the bulb light up, we need to ensure the circuit is closed. That means connecting the cell, wire, and bulb in a continuous loop so that the electrical current can flow freely through the entire circuit. Using proper electrical symbols when drawing these circuits helps us visualize the connections clearly and accurately. So, completing the circuit involves making sure that there's a complete path for current to travel from the positive terminal of the cell, through the wire and the bulb, and back to the negative terminal of the cell. This continuous loop is what allows the bulb to light up when the circuit is complete. And understanding this is fundamental to controlling when and how electrical devices operate. Now, let's look at what happens when we complete the circuit. First, if the circuit isn't complete, the bulb does not light up. This is because electricity can't flow through an open pathway. But once we close the circuit, allowing the current to flow freely, the bulb lights up. This demonstrates the importance of a complete circuit for electrical devices to work properly. It's a simple yet fundamental concept that ties into the overall idea of how electrical circuits operate and power our devices. Now, with the help of your teacher or carer, it's time to put your ideas to the test. We're going to see if your suggestions and diagrams actually work to light the bulb. For this, you'll need some real batteries, a small light bulb, and some wires. The key here is to create a complete circuit. That means making sure the electricity can flow from the battery, through the wires, and into the bulb, then back to the battery. This hands-on activity helps you understand how circuits work in real life, beyond just drawings. Remember, testing your ideas is a crucial part of learning about electricity, and working with someone else makes it safer and more fun. So, let's carefully connect everything and see if the bulb lights up. That's the moment where all your planning and diagrams come to life. Let's take a closer look at some materials and how they interact with electric charges. For example, a diamond, a rubber tire, or a rubber balloon. These are all examples of insulators. They resist the free movement of charges, meaning that if you try to move electric charge through them, it's much more difficult. That's why insulators are great for preventing the flow of electricity and protecting us from shocks. On the other hand, we have conductors like copper wire and silver spoons. These materials allow charges to flow freely through them, which makes them perfect for conducting electricity. That's why copper wire is commonly used in electrical wiring, and silver is known for its excellent conductivity. So, the key difference here is that insulators resist charge movement, while conductors facilitate it. Understanding this distinction is crucial because it helps us choose the right materials for safe electrical systems and devices. It's all about controlling where and how electric charges move, which ties directly into the overall theme of understanding electrical conductivity. Can you think of any other conducting materials besides copper wire and silver spoons? It's a great question because many materials can conduct electricity, not just metals. Think about things like aluminum foil, iron nails, or even certain types of pencils that have graphite in them. Now, I want you to consider how we can test whether these materials can actually make a light bulb glow. With the help of your teacher or carer, try experimenting with your suggestions. Use real batteries, a small light bulb, and some wires to see if your chosen materials complete the circuit. This hands-on approach is essential because it helps you understand the concept of electrical conductors practically. Remember, the key is to see if the material allows electricity to flow through it and power the bulb. So, I encourage you to try different materials and observe what happens. This activity ties back to our overall theme, understanding what makes a good conductor and how we can use that knowledge in real life. So, what can electric circuits actually do? Well, for starters, they enable the cooling system of a refrigerator to work. Without circuits, our food wouldn't stay fresh for long. They also help trains move, making our daily commute to work or school much easier and more efficient. Electric circuits are what allow light bulbs to light up, giving us illumination when we need it most. And beyond lighting, they also help specific devices produce heat and sound. Think about the heaters and speakers we use every day. All these examples highlight just how crucial electric circuits are in our daily lives. They're not just a part of technology, they're woven into the very fabric of how we live and move around. So, understanding how they work helps us appreciate the many ways they make our lives easier and more comfortable. Let's wrap up with a quick review of what an electric circuit really is. An electric circuit is made up of several key components, including wires, a light bulb, and a power source like a cell or a battery. These parts work together to create a complete path for electric current to flow through. The most important thing to remember is that a complete circuit features an unbroken loop. This means that charges, or electrical energy, can continuously flow around the loop without interruption. When the circuit is complete, the electricity can power devices like our bulbs and other appliances. Understanding this loop is essential because it's the foundation of how all electrical systems work. Without a complete circuit, the flow of electricity stops and devices won't operate. So, in essence, a circuit is all about creating that continuous, unbroken path for current to travel smoothly and power our everyday technology.